Hello there. So let's take a look at experiment 1 and some of the ideas we'll be looking at in lab today. So the chapter is heavily based on the metric system. We have distance, we have mass, we have volume, and then connected to that we have measurement of temperature and being able to convert from one unit to another. You're going to be measuring the sizes of pieces of paper tonight and calculating the area of the paper. A measurement system for distance has the meter as the base unit. 1,000 times bigger than a meter is a kilometer. 1,000 times smaller than a meter is a millimeter. 1,000 times smaller again, so 1,000,000 times smaller than a meter is the micrometer. But for measuring the paper, we're really more interested in this in-between unit known as centimeters. There are 10 millimeters to make a single centimeter and 100 centimeters to make 1 meter. And that gives us the conversion from meters to millimeters of 1,000. 100 times 10 gives us that overall conversion factor of 1,000. From centimeters, which you'll be measuring on a ruler, you can convert into millimeters by taking the centimeter value and multiplying by 10. If you start with a bigger unit like centimeters, converting into a smaller unit, starting with the bigger unit, you multiply to give a bigger answer. Meanwhile, with the centimeter value converting into meters, you're starting now with a smaller unit, so you're going to finish with a smaller answer. So that conversion factor of 100 means that the centimeter value will be divided by 100 to convert into meters. Or if you're looking at the millimeter values you just converted from centimeters, you can take the millimeter value, which is a smaller unit than a meter, and you can convert with that factor of 1,000 by taking the initial answer in millimeters and dividing by 1,000. If you're starting with a smaller unit, you're going to finish with a smaller answer. If you start with a bigger unit, you're going to finish with a bigger answer as you convert to centimeters or millimeters. Remember, when you do that calculation for the area of the paper provided, that answer should only be as precise as the least precise piece of information you have. So the initial piece of data with the least number of significant figures should be the number of significant figures you use in the final answer. You'll also be doing some conversions in temperature. Looking at the initial temperatures in Celsius, you can convert into Fahrenheit by taking the Celsius value, multiplying by 1.8, and then adding on 32 to give the Fahrenheit equivalent. Or, if you need to convert a temperature in Fahrenheit back into Celsius, you take that initial value in Fahrenheit and perform the reverse calculation in the reverse order. So now you're subtracting 32 first and then dividing by 1.8 last to convert back into Celsius. To convert into Kelvin, we'll take that original Celsius value and we'll add 273 to give us a Kelvin equivalent. Kelvin values are never negative and are always bigger than the Celsius value by 273 units. Now, when you're looking at these measurements and working out the significant figures, remember that non-zero numbers like 1, 2, 3, 4 are always significant because there's something being measured there. The tricky part is with the zeros, and they fall into 3 classes. As you look at your values from left to right, the zeros at the beginning, before we see the first non-zero number, in this case 9, those zeros at the beginning in red, they are never considered significant. Always ignore them. Zeros in the middle in green, which have non-zero values to the left and non-zero values to the right, they are always considered significant because there's real data, real measurements to either side, so we always include the zeros in green. The zeros at the end in blue are the tricky ones. Sometimes they're included, sometimes they're not. You'll only include them if there's a decimal point somewhere in the number. It could be further to the left, or it could be further to the right, but it's got to be there. If it's not, then we don't include the zeros at the end in blue. So never include them, always include, and only include if there's a decimal point. You can look at your Chem Talk videos for more examples on this kind of thing. Be aware, however, that when you're making a measurement using your eye, visually, there's always a degree of uncertainty about the value. And it depends on how accurate your method of measuring is. But there's always going to be uncertainty. And that comes with you having to estimate that last significant figure in the value. Let me show you what I mean. If we look at this strip of paper here in the middle, imagine we're using the ruler A to measure the length of this piece of paper. We can clearly see that it's 1, 2, 3, 4 centimeters, but not quite as long as 5 centimeters. So 4 is a certain part of the measurement, and the uncertain part is down to 0.1 of a centimeter, which you're going to have to guess. And looking at that, I would estimate or guess it as 4.8 centimeters. The 8 is your estimate, because we don't have a measurement on the ruler to show us that. If we use a more accurate ruler, which has centimeters and millimeters, we'll make a more accurate measurement of the strip of paper, but there's still going to be uncertainty. We can see it's still clearly 4 centimeters. We can even see that it's clearly 1, 2, 3, 4, 5, 6, 7, 8 millimeters, but it's a little bit more than 8 millimeters. And so there comes the uncertainty. So I would estimate it as 4.82 centimeters. We can clearly see that it's 4 centimeters. We can clearly see that it's 8 millimeters. But it's somewhere between 8 and 9 millimeters for the end of the piece of paper. And that's where our estimation of that uncertainty comes into play. So with visual measurements you have to make with your eye, you always have to estimate that last level of precision. So for example, looking at our beaker here, it's a beaker which measures volume in 10 milliliter increments. So we'll go to 100, 110, 120, and you can see if you look closely it's a little bit higher than the 120 milliliter marking. So we have to estimate between 120 to 130. It's only just over, so my estimation of that uncertainty is 1, giving us 121 milliliters in total. We can clearly see it's 120, so that 1 in 121 is where our estimation of the uncertainty comes in. If we look at the next one with a graduated measuring cylinder, it's more accurate, but there's still uncertainty. It's clearly 50, 51, 52 milliliters in volume, but it hasn't quite reached the marking for 53. And so here's where uncertainty comes in again, between 52 and 53, and because the lower edge of the water level at the bottom is almost at 53, so a final value of 52.9. So the measurement here of 200 grams, we would include the zeros after the 2 because of the decimal point. So it's 5 significant figures in total. Now, we also have some measurements on density. Remember, density is a physical property. We're measuring a mass in a given volume, and it's showing us how literally dense that matter is. But the density has to be measured at a steady constant temperature. And that's because at different temperatures, the kinetic energy of the molecules change. So if we look at a sample at, we'll say, 20 degrees Celsius, and if we have marked this area for the measurement of density in our little cartoon here, we're just measuring the mass of those molecules in blue for that given volume. Mass divided by the volume gives density in grams per milliliter. However, if we were to increase temperature, that would see an increase in kinetic energy. And those molecules would move faster, and molecules which move faster naturally spread out and take up more space. So now 1, 2 of our molecules, which we had originally measured, are no longer in that given volume. The density has decreased as temperature increased. Conversely, if we were to drop temperature from the original 20 degrees Celsius, molecules have less kinetic energy as temperature drops. They're moving more slowly, and molecules which move more slowly naturally take up less space. So it's a little bit like imagining a middle distance running race at an athletics meeting. If the person in the front slows down, it kind of crunches up the pack. So those molecules in green, which we previously weren't measuring in a unit volume, are moving more slowly and are now included in that unit volume space. There's more mass in that given volume, so the density increases as temperature decreases. So let's take a look at some of the experiments you'll be performing. The first one here, looking at the accuracy of a graduated measuring cylinder compared to a flat bottom beaker, which is inaccurate in its measurements of volume. So here I am. We'll take a flat bottom beaker, probably a 150, and we're going to add water until the mass is 40 grams. Tare or zero the balance before you start adding the water. So now you're just measuring the mass of the water itself. Get it as close to 40 grams as you can. You can see here I stopped at 40.04. Now we're going to look at the volume in the beaker from that 40.04 grams. You can see I've also added a little bit of dye so we can see the water level a bit more clearly. So I did cheat a bit just for the sake of the video. And our 40.04 grams of water has a volume, well there's 40 there and there's 60, so it has an actual volume of about 49 milliliters. I think that's slightly less than halfway between the 40 and the 60, so I'm going to judge that as 49. So that's what the flat bottom beaker thinks the volume of this liquid is, 49 milliliters. However, flat bottom beakers are not accurate. We need a graduated measuring cylinder to judge the volume of this liquid. Graduated measuring cylinders are much more accurate. And so if we take a look, we can see it's just slightly shy of 40 milliliters. I'd probably call that 39.9 milliliters. So here's a calculation for the inaccuracy of the flat bottom beaker. The beaker itself measured a volume of 49 milliliters. The graduated measuring cylinder gave the accurate measurement of 39.9. So the difference between the beaker and the graduated measuring cylinder is 9.1. We divide that by the actual accurate measurement of the graduated measuring cylinder of 39.9 times 100 to turn it into a percentage. But because one of our calculations has just two significant figures, our final answer should be two significant figures, so we round up to 23%. So let's look at the calculation of the density of the soda cans. At the sink, you can take one of the litre beakers and fill it up to the brim with water. Remember, the flat bottom beakers are inaccurate, so we need an accurate measurement of the water volume in one of these beakers. Fill it to the brim till it overflows, and then start decanting this liquid from the beaker into the graduated measuring cylinder. You need a steady hand. We don't want to lose any of the water that's in that beaker when it's to the brim. And so it's going to take multiple fills. And of course you can only measure 100 milliliters at a time. You don't have to measure 100 milliliters each time. You could measure just 92 or 94, dispose of that in the sink, then fill up the graduated cylinder again, keep going, and keep a tally of the volume until that flat bottom beaker is empty. You'll probably find that the actual total volume of the beaker is very different from the volume mentioned on the side of the beaker. Fill it again right to the brim, only this time you're going to put one of the soda cans in. If it's a soda can which floats on the surface, the one that's less dense in the water, make sure to dip the can under the water level, but only just, so that we measure the full volume of the soda can. The volume of the soda can is displacing water from the beaker. So the volume of water remaining is the difference between the full beaker and the beaker after it's had a soda can added. Remember, the mass divided by the volume gives us the density of the soda can. The volume of the soda can is the total volume of the beaker minus the volume of the beaker when the soda can was put into the beaker.